Stars in our firmament have ages given man a feeling to believe our feet firmly planted on a solid earth with a protective heaven. But science has continually whittled away at this idea. For some time, we have known that our earth, in reality, is only a changing ball of rock and soil, water and air, spinning and whirling in space around our sun. And even as a planet, we are not very special, being only one of 9 in orbit around the mother sun. Our sun itself, a star and only a small middle-aged one as stars go, is a kind of lost child on the outskirts of its galaxy, which we can see in the sky as the Milky Way. It is only one of hundreds of billions of stars in our galaxy, which is only one of hundreds of billions of galaxies, all of which are in constant motion. If we are not unchanging in space, neither are we eternal in time. Our sun, 5 billion years old, will, in another 5 billion years or so, burn itself out, and in doing so, expand and absorb all its planets as countless other stars have done before. Our sun's only real distinction that we know of thus far is that it has people whirling around it. The question is, might this have happened elsewhere in the universe, or are we alone? It was recently discovered that stars and gases in space emit natural radio waves which can be picked up and amplified by radio telescopes. The Jodrell Bank Radio Telescope in England, the Green Bank Radio Telescope in West Virginia, and this one at Arecibo in Puerto Rico can be called man's largest ears. The bowl of the telescope, 1,000 feet across, made of half-inch wire mesh, acts as a reflector, able to focus even extremely weak radio signals from space. In searching for life on other worlds, the theory is that intelligent civilizations in the universe would use natural radio frequencies as a means of communicating with one another. By listening to signals from interstellar space, intelligent codes could be distinguished from the patterns of natural radio waves. Radio astronomer of Cornell University and director of the Arecibo Ionospheric Observatory, Dr. Frank Drake, conducted Project Ozma, the first search for intelligent life in space by radio telescope.
Some years ago, it was suggested by Professors Morrison and Cacconi at Cornell that there might be other civilizations in space attempting to send us messages. We use very sensitive and ingenious detecting devices to search for intelligent signals amongst the static which comes to us from the interstellar space. So in 1960, we made a short search for such signals with existing telescopes, such as the 85-foot telescope at Green Bank, using the 21-centimeter line frequency. And we looked at, there was time, in fact, to look at only 2 stars. The ones we picked, of course, were the 2 nearest stars, which are like the sun. The stars Tau Ceti in the constellation of Cetus the Whale, and Epsilon Eridani in the constellation of Eridanus. We found no evidence for extraterrestrial intelligence signals. But now we must realize that this was an extremely limited search, and the fact that we found nothing should not discourage us or cause us to think that any future search is going to fail. One can estimate that a search which has a good chance of succeeding will take perhaps 30 years. But if one is going to make a realistic search, this is what is required. And anything less than this is really not worth the effort because the chance of success is so small. Surely the results of the detection of extraterrestrial signals are going to be one of the most exciting things that ever happened.
While some scientists in the discipline of astronomy press the search for intelligent life in the distant stellar regions beyond our solar system with the big ears and eyes of the radio and optical telescopes, some, perhaps more, feel they would be making an historic discovery by a less ambitious find. These men are called exobiologists. They are looking for microbiologic forms of life, lesser than intelligent man, and perhaps higher than the lowly virus, something between the organic molecule and the bacteria that might have evolved outside the Earth. The most likely candidates for such a search are the planets Mars and Venus, Earth's nearest neighbors in the solar system. The Mariner spacecraft has been our principal vehicle for unmanned planetary exploration. The planetary program is carried out by the Jet Propulsion Laboratory operated by the California Institute of Technology for the National Aeronautics and Space Administration. Dr. William H. Pickering is the director.
Mars and Venus, of course, are the two closest planets to the Earth. In some ways, we know more about Mars than we do about Venus, because Venus is always covered with clouds. We do not believe we have ever seen down to the surface of Venus, that is with a telescope from the Earth. Whereas in the case of Mars, we usually see the surface of Mars. Mars, on the other hand, is a planet which astronomers for many years have compared with the Earth. The size is a little smaller than the Earth. It happens that the day on Mars is almost exactly the same length as the day on the Earth. The year is about twice as long as the year on the Earth. The seasons change in the same manner that they do on the Earth. In other words, the spin axis of Mars is tilted about the same way that the axis of the Earth is tilted. All of this has led astronomers to compare Mars with the Earth in many ways. And of course, the one comparison which one must always make is, what about life? Is Mars a suitable planet for life as we know it?
It is feasible, from what we know about life on Earth, that life could exist on Mars.
Dr. Richard S. Young, chief of the Exobiology Division of NASA's Ames Research Center.
On Earth probably arose as the result of a very sequence of events. We think we know what the primitive atmosphere of the Earth was like before there was any life on the Earth. We think we know what types of energies were available on the primitive Earth before there was any life on Earth. Biological evolution took over and the atmosphere was changed rather drastically until we have the sort of atmosphere we have on the Earth today, and we have the tremendous diversity of life that we have today. A subsequent result over the next, say, 3 billion years of biological evolution. In fact, then, just about any primitive planet during its early history should have undergone a similar sequence of events. They were formed obeying the same laws of physics and chemistry. They should have had the same type of primitive atmosphere and probably underwent chemical evolution in much the same way the Earth did. Now, what we need is proof of that.
If we can find life on one planet, say Mars, then it is very probable that elsewhere within our own galaxy, with life forms comparable to Earth.
The optical telescope has been the principal tool of astronomers for studying the stars and the planets from the days of Galileo centuries ago. The 200-inch mirror in the Palomar Observatory telescope in California can be called man's largest eye. It can bring into view the farthest observable objects in the universe, called quasars, points of light believed to be billions of light years away and moving away from us at incredible speeds. Another kind of telescope is the 26-inch refractor or direct view telescope, like this one at the United States Naval Observatory in Washington, D.C. To find planets comparable to Earth, revolving around stars comparable to our sun, Dr. Kai Strand, scientific director of the observatory, and his former colleague Dr. Peter Van de Kamp of Swarthmore College used a telescope of this type. They wanted to verify the argument that planets are abundant in the universe. In 1963, Van de Kamp announced the discovery of a planet orbiting a neighboring star, the first planet ever to be detected beyond our solar system, although it has never been directly seen.
Depends what you mean by seen.
Harvard astronomer Carl Sagan explains how the existence of this planet was deduced.
The second nearest star system after the sun is called Barnard's star, named after an American astronomer, E.E. Barnard. And the motion of this star across the sky is not a more or less uniform line on the background stars, as you might expect, but instead oscillates. And the wiggly path is due to the presence of a dark companion. We don't see the dark companion, but we can quite reliably deduce its presence from the wiggles in the motion of this star. Let's suppose this is Jupiter and this is the Sun, and the two of them are moving, of course, through space together. However, Jupiter is also going around the Sun. And when Jupiter is on this side of the Sun, its gravitational attraction pulls the Sun a little bit that way. When it's on the other side of the Sun, it pulls the Sun a little bit that way. And so, as the Sun goes through space, it has, in addition to its ordinary motion that way, it has, let's say, an up and down wiggle due to the motion of the invisible Jupiter. Okay? And so the wiggle tells you the presence of Jupiter. And not only that, it tells you its mass, and it tells you how far away it is.
If you were riding the nose cone of a rocket to the moon, this is what you would see as you approached the lunar surface for a landing. These pictures were made by television cameras in Ranger 9, the unmanned American picture-taking expedition to the moon in March of 1965. Since then, thousands of spectacular close-up pictures of the moon surface have been returned by Surveyor 1, which soft landed on the moon in June of 1966. Pictures from the probe of Lunar Orbiter in August of 1966 showed our planet as seen from the vicinity of the moon. This representation of the lunar landscape shows us what a man might see from the moon. A bright sun in a sky black as night due to the lack of light diffusion by an atmosphere, and the Earth visible in the lunar night hanging in its black sky like an oversized moon itself. Surveyor 1 and Lunar Orbiter returned much valuable information, and they have also shown us what we have known the moon to be: a body without atmosphere, without water, without life. Not unlike the moon in some aspects is Earth's neighbor in the solar system, the planet Mars. When, in July of 1965, the Mariner 4 spacecraft completed a successful Mars flyby after a journey of 8 months and 325 million miles, passing within 6,500 miles of the planet, 21 pictures of the Martian surface were returned to Earth, including one of the most remarkable scientific photographs of this age, Mariner's 11th picture of Mars. Many scientists felt that this picture settled once and for all the century-long controversy over Martian canals. In 1877, the Italian astronomer Giovanni Schiaparelli claimed to have seen canals which he thought could be evidence for intelligent life on Mars. As late as 1908, the American astronomer Percival Lowell confirmed the sightings. The spacecraft Mariner was too far away in its flyby to be able to show decisively what exists on the Martian surface. But most scientists agree that if life does exist there, it will not be intelligent but of a very low order.
Of course, the early astronomers saw canals, and they saw a lot of other things that...
Dr. Richard Young of Ames Research Center.
We no longer think canals really exist on Mars. We think they're primarily optical illusions, and then aren't something that the Martians constructed to transport water from the pole to the equator and keep the deserts wet and all that sort of thing. Mars has, although it's a harsh environment by biological standards, Mars has an atmosphere. It has a very rare atmosphere. It's a smaller planet, has a lower gravitational field, and its atmosphere is probably, something like 1/100th, or perhaps even closer to 1/1000th of the total pressure on the surface of the Earth. It also contains water. Life can't exist without water. The fact that Mars has water is terribly significant. Now, unfortunately, from a biological point of view, the amount of water in the atmosphere of Mars is very slight. It's about 1/1000th of the amount that one would detect in the Earth's atmosphere with a similar observation. There are other features of Mars that we're reasonably familiar with. Astronomers have been observing it for something approaching 100 years now, and they've known that there are light areas and there are dark areas. The dark areas are assumed to be, or at least by the early astronomers, were assumed to be vegetation. The light areas were assumed to be deserts. There are also pole caps on Mars, which have been shown to be water. However, although they're pretty extensive, the total amount of water in these pole caps is very slight. It's probably nothing more than a layer of frost. However, these pole caps do recede seasonally. In the spring, the pole cap recedes. At the same time the pole cap is receding or disappearing, the dark areas are getting darker, implying, at least to the early astronomers, that, well, water is becoming available now from the pole caps, and the vegetation in the dark areas is literally inhaling the water and is flourishing during the spring. We really simply don't know enough about the intimate detail of the surface of Mars to critically analyze any of these visual phenomena. All we can do is speculate about them. And so far, the best of our speculations has failed to demonstrate that life on Mars must be ruled out. In fact, the best of what we know still leaves well within the range of possibility the idea that life may well exist on Mars and would be well worth the search, if you will.
I feel that in the search for extraterrestrial life, there are three approaches. One, firstly, the one that you named, to go to Mars and see whether there's life there. The other one, which Frank Drake has for some time tried out, listening to radio communication from outer space. The third one is the one that we are working on here, retracing the path by which life appeared.
Dr. Cyril Panam-Peruma, chemist at Ames Research Center, is searching for answers to extraterrestrial life by studying the chemical evolution of life on Earth.
From the information we have today, we know that the Earth is 4.5 billion years old. Let me put that down as one of our starting points. 4.7 billion years is the exact date given. Life as we know it, or the first evidence of life in the fossil record, is about 3 billion. Now biology, or the Darwinian theory, takes over from here. See, you find the life evolving into a whole variety of organisms. We know that mammals are around 160 million. And then so on, we come to the evolution of man, finally. What went on before this? From the time the Earth was formed, or even further back, from the time the solar system was formed. This can be described as chemical evolution. We know that the solar system is about 5 billion. And then, if you go backwards in time, you come to the origin of the universe, which is greater than 10 billion. Some put it at 13, some at 20, but we know definitely it's more than 10 billion years. Now we have some starting points to go on. We know that 90% of the universe is hydrogen. Right. So the hydrogen then, by a series of reactions during the birth of a star, gave rise to the other elements of the periodic table: carbon, nitrogen, oxygen, and so on. In other words, you would have thermonuclear reactions taking place within a star. So the idea of chemical evolution then is a gradual evolution of hydrogen, the initial matter of the universe, to give the elements of the periodic table, to give the constituents of the early Earth atmosphere, say methane, ammonia, and water. Simple chemistry tells us that the carbon will be in the form of methane, the nitrogen will be in the form of ammonia, and the oxygen will be in the form of water. So the early atmosphere of a planet would have been made up of methane, ammonia, and water. From here on, we visualize what happened. The early atmosphere being acted upon by lightning, ultraviolet light from the sun, or heat, producing organic molecules, till the early oceans became something like a primordial soup. So from a primitive atmosphere, we are hoping to go to the stage when the two molecules that are important to living things, the nucleic acid and the protein, were formed. First molecules capable of replication. So it's a stepwise process. It appears to be a beautiful plan going all the way from the hydrogen atom till the time you get to the intelligent human being. So it is a coherent story. It is something which appears most logical. It is rational. So the discovery of life on Mars to people studying the origin of life will be the greatest thing. As a matter of fact, in my mind, the search for extraterrestrial life is only part of the question of the study of the origin of life. This is the scientifically broader question, origin of life in the universe. And going to Mars is the unique opportunity that we have of, perhaps the one only opportunity that we have of showing this, because if there's life on Mars, and especially if we can show that its origin was different from the origin of life on Earth, or it was independent, then we'll have a very heartening answer to this question of uniqueness in life.
New York Times science editor Walter Sullivan, author of the book on which this program is based, raised this question with Nobel Prize-winning chemist Dr. Harold Urey.
Dr. Urey, a lot of the discussion on the origin of life boils down to the question of whether there are other worlds, other solar systems. You believe there are.
It is my belief that if you have conditions such as we have on the Earth, life will spontaneously appear. I don't know how long it takes, maybe a million years, maybe a billion years, but sometime life as we know it will appear. Every indication is that the properties of the elements in the most distant stars that we look at are the same as those that we have on Earth. The physical universe is the same everywhere. That is our conclusion. The laws are the same as far as we go, as we understand them. And this, of course, means that the chemistry of carbon, nitrogen, oxygen, hydrogen, the four abundant elements in living things, the chemical properties of these elements will be the same wherever we are in the universe. And therefore we expect that they will have the capacity to evolve into what we would call living organisms, no matter where we go. Now, we don't expect that they will be the same.
Sometime in 1973, a spacecraft will take off from Earth. Its name will be Voyager. The Voyager, a new kind of space vehicle, will begin a trek to the planet Mars. The first of a series of missions that will eventually carry sophisticated life detection devices to the Martian surface. The success of a Voyager mission would be a scientific breakthrough in our unmanned planetary program. It will be our first attempt to soft land an instrument package on another planet. Looking beyond Voyager to 1977, 1979, and the 1980s, space engineers are already at the hard, practical model stage of designing devices that are still emerging from the minds of scientific dreamers. One such device designed for a Mars life search is the Automated Biological Laboratory called an ABL. One concept of it has been developed by the Aeroneutronic Division of the Philco Corporation. It would operate remotely and automatically on Mars, so says space research engineer William Hostetler.
But basically, there are several processes that have to be performed. First, of course, you have to obtain physical samples of the surface of Mars, physical samples of the soil, because that's where the organisms will congregate if there are living organisms. I might comment, incidentally, that we are concerned more with the lower forms of life, the molecular forms of life, rather than elephants and horses and so forth. We are prepared to take pictures of these things if they happen to be there. The ABL is divided really into three basic integrated subsystems. One of these is the sampling subsystem that is used to obtain the surface samples from the soil samples from the surface of Mars. At the very bottom of the ABL and directly underneath, there is a system that uses a brush and vacuum system to obtain samples of the Martian surface directly under the ABL. Also, there is a core drill system that drills into the surface about 10 feet to obtain subsurface samples in case the water availability or other conditions make it more likely as a place for Martian biological life. A second system picks up samples around the ABL with a sampler, as you see here, which is located on a linkage that attaches it to the main body and will pick up samples from a system is used for getting samples from a considerably further distance, and in particular selected areas that the visual survey system has pointed out as being particularly desirable because possibly they are warmer than the surrounding spots, or they have a different appearance that might appear to be vegetation or something of that nature. So a sampling line is deployed ballistically, fired out like a small rocket, carrying this line to some distance, up to possibly 1,000 feet from the ABL location. And a sampler, then, similar to the one that works in the vicinity of the ABL, is carried up on an elevator, latched onto a trolley on this line, and deployed out to the desired spot to obtain the surface sample, returning and delivering it to the operating parts of the ABL. These samples are then processed and brought into the interior of the ABL for chemical processing prior to reading out the experiment. The chemical processing equipment is located generally in the central area of the ABL in the form of 13 chemical processors located circumferentially around the central core. Certain supplies, water, certain gases, are stored in tanks around the center of the ABL. Other chemical reagents are stored in ampules, which hold individual quantities in this area that surrounds the processors. These ampules are put into cartridges like this so that they feed to the outer end and can be picked up by the processing by the transport device, which internally then moves them to the proper location to conduct the chemical analysis. After the analysis is completed, the samples are then transferred to the instruments to read out the experiment results. The data from these are then processed internally and transmitted through the high-gain system back to Earth.
If scientific and engineering problems that must be solved to accomplish this feat are not overwhelming, the political obstacles may indeed be insurmountable. Congress will soon have to make the most important decision on space policy since President Kennedy first won approval to commit us to the space age. Mr. Walter Sullivan.
What a wonderful planet is our world, and how far it may be to anything else like it. We have reason to believe there are other planets blessed with our advantages, a kindly, stable parent star, a well-placed orbit, a suitable atmosphere, dry continents for advanced life forms, great seas within which their primitive ancestors evolved. But the fragile green hue of life appears only here and there on our planet as seen from space. Its hold is tenuous. If inbred passions overcome reason, we can now render the planet uninhabitable. Is that the fate of all technological societies? It is up to us on this wonderful world of ours to prove that it is not so.